So we're going to look at 4.5. We're only going to look at linearization and differentials. So we do not need to do Newton's method because it is not on the AP exam anymore. It is on CHS, so we're going to take CHS. So we're going to skip over it. So the warm-up says a line passes through the point 25. It has a slope of 0.42. Write the equation of the line. So it's basic algebra. You go back, you write your equation in point slope form. So equation of the line would be y minus 5 equals 0.42x minus 2. Then it asks you what is the value of y when x is 2.3. So if I wanted to know the y value when x was 2.3, we would solve the equation for y. We would plug 2.3 in for x. So I'd add 5 to the other side and put 2.3 in where my x is. So then I get 0.42 times 2.3 minus 2, which leaves you with 0.3 plus 5. So 0.3 times 0.2, or 0.3 times 0.42. You could go and multiply out using old school like multiplication. 3 sine 42 times 3. And then you counted your decimals. You got 0.126. And then you add that to 5 and you say, okay, well then y equals 5.126 when x is 2.3. And logically, that should make sense to you because if the original point was 2.5 and now you're looking at the point 2.3, then x went up to 5.126. So both x and y increased and they increased together. So it says how much does the y change when x changes by 0.3? Well, the y changed by 0.1. So why are we looking at that? What does that kind of reflect or relate? Well, what that ultimately is coming down to is linear approximation. We are going to approximate complicated numbers and complicated equations using lines. So we're going to find equations of tangent lines. We're going to find them at simple points that we can calculate and then use them to calculate more complicated points. So the change is that 0.126. If you were to write out 0.126 and multiply it by 0.3, guess what number you're going to get? At 0.42. Because that 0.42 ultimately comes back to it as a slope. So change in y over change in x ultimately comes back to our slope. So again, everything is sort of coming full circle and we're comparing. So why do we use the points of a tangent line? The tangent line, as we know, represents a curved slope at a particular point. So we use tangent lines in calc to represent slopes at points to look for the change in the problem. We're also going to use them for something called being locally linear. It's also known as linearization. It's also known as linear approximation. So we're going to take something complicated, like a square root, we're going to find its equation of a tangent line. So we have a square root, we're going to find its equation of the tangent line, and then what we're doing is we're taking that square root, we are zooming in infinitely close to that particular point where the reds and the blues meet, and what happens is as you zoom in closer and closer and closer, the red and the blue look like they behave identical. So that's what we call linear approximation, is zooming in further and further and further until the two functions look like they behave as one. Here's like the formal definition of linearization. So the formal definition says if f of a is a differentiable function at the point a. So we have function f, it's differentiable in a. Then we have the equation of the tangent line, but now we're modifying the equation slightly. So instead of being y equals, we're going to call it L of x, where L of x represents the linear approximation at point x. So we're going to have L of x, where L of x represents the linear approximation at point x using point A. So point A is going to be a nice point on the function. We're going to use it to find a not so nice point. So in order to use linearization, we need a point on the curve, and we need the slope of the point at that curve. So in order to do linear approximation, we need a point on the curve, and we need the slope at that point. Back in the algebra days, we called those x1, y1s, and m. In the calc days, we're going to call them a, f of a, and f prime of a. So back in the algebra days, you plugged into point-slope form. And now in the calc days, we're going to replace the point-slope form as we knew it with f of a, and f prime of a. And then we're going to talk about what they mean in terms of calc. So x minus a represents the change in x to a. It represents the change in x to a. So we oftentimes refer to that as delta x. F prime a, x minus a, represents delta y. So then what we have is a tangent line that approximates delta y at any value of x. We talk about linearization after we talk about sketching curves, so you have an idea or an understanding of concavity. So I talk about curve sketching, then we talk about linearization, because we use the ideas of linearization with curve sketching. So if a function has a certain concavity, then that is going to affect if our linear approximation is an over or under estimate. So the concavity is going to affect if something is an over or under estimate. So if you looked at this graph right now, the black curve represents the original function. It's the black curve concave up or concave down. Is the red line, which represents the linear approximation, aka the tangent line, going to be above or below the black curve at the points we drew in? Above. So that would mean that my prediction I get from the red curve is going to be an over estimate, because all of my values are above the curve. So because all my values are above the curve, my predicted answer is going to just be a little bit more than the actual. So concavity affects our predictions. So if a function is increasing and concave up, then my prediction is an underestimate. If it is decreasing and concave up, it is still an underestimate. So concave up is going to be an underestimate. So up is under. Both start with U. Up, under. Concave down is an over estimate. So down and over both have O's. Up, under, U. Over, down, O. Any better tricks to help you remember? So consider the function the square root of x. We know that the square root of 4 is 2. But without a calculator, how could we calculate something other than a perfect square? So that's ultimately what this is going to come down to. If we want to calculate something that is not a perfect square, how do we do it? So if we want to calculate the square root of 4.1, we are going to use the equation of the tangent line at the pretty point we know to predict the point we don't know. So we're going to say that L of x equals f of a right? So that is our new formula. So in this case, f of a is 2. F prime of a, we need to calculate. F prime of a is going to be f prime of x. Well, in this case, f of x is root x. So its derivative is 1/2 x. So the negative 1/2. And we want to know what it is at 4. Because in this case, I'll write it in my a is 4. So this is like f of 4 plus f prime of 4 at x minus 4. So that's where you get 2 plus, again, f prime of 4, which is 1 over 2 square roots of 4, which is 1 over 2 times 2, or 1/4. So the linear approximation for this function is as follows. Then what we want to do is use L of x to predict 4.1. So L of 4.1 equals 2 plus 1/4. 4.1 minus 4 equals 2 plus 1/4 times 0.1. The 0.1 is like 1/10. So a 10th times a fourth is 1/40th. So you get 2 and 1/40th. So again, square root x, you would say, is concave down. It's increasing. So is that answer of 2 and 1/40th going to be an over or under estimate of the actual? Perfect. So we predict that this is an over estimate. Let's see what the actual value is. So you take a calculator, type in the square root of 4.1. Okay, you get to 0.0248. I personally, off the top of my head, don't know what 1/40th is. So our answer was 2.025. So comparing them, 0.0248 versus 0.0245, was our prediction pretty close? Yes. Is it just slightly an overestimate? Yes. So now, next time somebody asks you to find a complicated square root, you can find the answer. Because I know that that's what you've always wanted to be able to do. That is like today's lesson. That is what we are looking at, comparing, etc. So what I have for you here is the graphs, right? So the red graph represents the square root function, the blue graph represents our tangent line. So again, you can see exactly what I put in that table for you. Red's concave down and increasing. The blue tangent line is always above, therefore an overestimate. And then we already did that, use a calculator to approximate. Okay, find linearization, L of x to f of x for, it's been forever since I think we looked at one of these, a natural log of x plus 1 at x equals 0. So we are trying to approximate 0.1 given 0. So that means my a value is 0. So I have f of 0 and I need f prime of 0. Those are the two key points I need to plug into L of x. So f of 0 is the natural log of 1. Natural log of 1 is equal to, The derivative of the natural log is 1 over the inside times derivative of the inside, which is 1. So f prime of 0 is 1 over 0 plus 1, so 1. L of x thus becomes 0 plus 1 times x minus 0. So L of 0.1 becomes 1 times 0.1 minus 0, which is 1/10. Is the natural log function concave up or concave down? Or concave, I have no idea. Think of the fact that the natural log is the inverse of an e function. So it's an e function log. Good. So like e of x, right? Also a little off, but that's what e of x looks like, right? So the natural log of x is its inverse. If you think about inverses, they're typically reflected across the equation y equals x. So like inverses are reflections across this. So then if you have to reflect that, so does that. So is that going to be concave up or concave down? Concave down. So concave down is going to be an inverse. And just to give you an idea, natural log of 1 plus 0.1 is 0.0953. So again, my 0.1 compared to 0.0953 is a little bit over. Use linearization to approximate the square root of 123 and the cube root of 123. What makes this one harder than all the last ones? They don't come outright and tell you f of x. So what would f of x be? And again, you kind of have two problems happening here. Because I have this problem and that problem. So what's the f of x of the blue problem? What would my equation be for that side? And then on the red, it would become, yeah, awesome. So I have two different functions now. What do I need to be able to use linearization? I need nice numbers for these points. So I need an f of a for the blue and an f of a for the red that are nice numbers near the given problem. So I'm given 123. So what's a nice square root near 123? Perfect. So we want to find f of 121 So my A is going to be 121. My f of A is 11. So then that also means I need f prime of A. So at this point, square root of x, hopefully we just have started to memorize, is 1 over 2 square roots of x. So then f prime of 121 is 1 over 2 square roots of 121, which is 1 over 2 times 11, which is 1 over 22. So we want to approximate 123. So we're going to do L of 123 equals f of a, which we said was 11, plus f prime of a, which we said is 1 over 22, times x, which was the given value 123, minus a, which was 121. So 123 minus 121 is 2 divided by 22 is 111. So 11 plus 111 is 11 and 111. The square root function is concave. Therefore, this is also an over. So square root of 123 is 11.0905. 11 and 111 is 11.0909. So you are off by 0.0004. That's how good linear approximation is. Okay, how about the red function? So now we have a new function, right? Now we have the cube root. We haven't talked about a cube root yet. So we want to use linearization to find the cube root of 123. So that means I need a perfect cube near 123. So what's a perfect cube near 123? So we want to use f of 125. That also means I need f prime of x. So now I have to find the derivative of the cube root of x. So 1/3 x to the negative 2/3 equals 1 over 3 x to the 2/3. And then I need f prime of 125. So 1 over 3. 125 to the 2/3. So here's the thing, guys. Take the cube root before you square 125. Because the cube root of 125 becomes 5. 5 squared becomes 25 times 3 becomes. So you can do that math in your head. You just have to make sure you pick the order of operations that fit you. Like, you know what I mean? Sometimes if you see 125, you're like, yeah, I'm going to square that first. And then I'm going to cube it, or cube root it. And then it's like, oh my gosh, my numbers are really big. I can't do that. Okay? So, L of 1, 2, and 3 equals f of a plus f prime of a times x minus a. So this is the first time that when I did an x minus a, I actually get a negative, which is okay. It just means that my number, or my answer, is going to be less than my nice pretty point. And that again should make sense because my nice pretty point is 125. I'm predicting 123. Well, the cube root of 123 should be smaller than the cube root of 125. So I get 5 minus 2/75, which is 4 and 73/75. Which again is probably 4.9 something, right? Like it's going to be pretty decently high. Yeah, 4.973. Now, the cube root. Does anybody know what the cube root function looks like? Remember, it's the inverse of the cubic function. So cubic function looks like that. So if you have to invert it or collect it, the cube root function is going to look like, not bad. Let's go backwards then. Just gonna kind of look like that. So do we predict that to be truncate up or truncate down at the point we're predicting? Yeah. So that means for the first time, this answer is going to be an inverse. Okay. I mean, we can't do these without right? So you have f of x is tan x. We're looking at the tangent at -5/4. So we are going kind of backwards on our unit circle. We're predicting it at -5/4 plus 0.1, which is a non-unit circle value. So we need to know a whole bunch of stuff. That first thing I need to know is f of a and f prime of a. So f of a this one's not bad. Tangent of 5/4 is 1, so tangent of -5/4 means we're in quadrant 4, so it's going to be, I wasn't so troll. What do we need to know now? Well, I need to know f prime, because I need to know f prime of a. So it's the derivative, and I know it's been a while, of tangent. Secant. And then I need to know f prime of -5/4. Well, secant is really 1 over the cosine. Cosine of 5/4 is really, yeah. So, and because it's squared, do I have to care whether my root 2 over 2 is positive or negative? Because anything squared is, so you get 1 over root 2 over 2 squared. So you have 1 over root 2 squared, which is 2. 2 squared, which is 4. So 1 over a half becomes a 2. So my slope is 2. My point A is 5/4 and -1. So my L of x at -5/4 plus 0.1 is f of a, -1, plus f prime of a, 2. My new point we're investigating, -5/4 plus 0.1, minus the point we used to start, -5/4. So what happens when you have minus a minus? Comes a plus. You have -5/4 and +5/4. They are additive inverses, therefore you get so we get -1 plus 2 times 0.1. So -1 plus 0.2 gives me -0.8. If we say that f prime is decreasing from -pi to 0, is the approximation going to be less than or greater than the actual value? So if the derivative is negative, so I don't know about f of x, so let's say we just don't know really, but f prime is decreasing, what does that tell me about either f or f double prime? So if f prime is decreasing, f double prime has to be negative. If f double prime is negative and f prime is decreasing, then my original function is, and if f is concave down, then this is an curve. So if you don't know what the function looks like, you could actually take f prime, and then find f double prime. So I could have found the derivative of secant squared, which is 2 secant x, because it's the chain rule, right? So 2 inside times derivative inside, which is your secant tan. So I would end up with secant squared, only because I'm running out of space, tan x, and then what you could do is find that value at this point, and then use it to be positive or negative to determine concave up or concave down. So like if you don't know what a function looks like, you don't have a graphing calculator, but you need to know if it's an over and underestimate, you could compare the value of the second derivative. If it's positive, concave up. Negative, concave down. So that's kind of what I was getting at with this question here. And then that is it for today. Homework is going to be in the textbook. It is on, I believe, I put a note on here, 242. Let's confirm. Okay, so 254 actually. So we're going to look at 1 to 5. And 11 to 14. That's it. 1 to 5, 11 to 14. So not even any problems here. My book, but there's actually no answers on either section. Yeah, like my answers are all at the top or like all at the bottom, so if you only figure 1 to 5 and 11 to 14, you wouldn't have anything you shouldn't have.